Hi, welcome back to Software Analysis and Design. Today we'll talk about domain analysis, about class models and class diagrams. That's the notation that we will use to express our domain models. Let's see, what do we have here? We're going to start with our assigned reading, and that was the Characterizing Classes by Rebecca Wurzbrook. And then we'll move into domain analysis and models, and then talk about class models and diagrams. And eventually, I'll propose 2 exercises that you can work with to improve your understanding of domain classes. Let's jump into the Characterizing Classes reading assignment. This was an IEEE software article, and on the right-hand side, you see a quote by Rebecca Wurzbrook. It says, "Take time to find, study, and learn about well-designed code and systems. Learn what makes one code base more easily maintained than another, or what makes one easier to understand or test. Read other people's code. There's a lot you can learn." Even if you go back to your own code that you wrote a year ago, you may learn something. If you go look at other people's code, even more so. So continued peer review in whatever coding assignments you do is super beneficial. Rebecca wrote this really cool book on object design where she speaks about roles, responsibilities, and collaborations. And this IEEE software article for today essentially captures the most important points of the book. I'm not going to say don't read the book. It's certainly a good book. However, here is kind of a short abstract version of it on how to characterize classes. She starts with saying there are many ways to understand the nature of a class, but I start looking at its name. Ideally, the name that you give a class is something meaningful, so that would give you a good understanding of what the purpose of the class is or what it represents. And then she goes on to explain that purposeful oversimplifications or role stereotypes from responsibility-driven design can help identify and understand the work that objects do. So there are role stereotypes that help us break down what the work of the objects is. We can use that knowledge in 2 ways. We can use this either in forward engineering or in reverse engineering. So forward engineering in this case means we use it as we go from use cases to class design. And reverse engineering would mean we look at a piece of code and then re-engineer the class design back out of it that's represented in there. Typical stereotype roles are the following. There is an information holder, which is an object that is designed to know certain information and to provide that information to other objects. There is a structurer, an object that maintains relationships between objects and information about those relationships. Complex structurers might pool, collect, and maintain groups of many objects. Simpler structurers maintain relationships between a few objects, and an example of a generic structure would be a Java hash map. It relates keys to values, so that's the structuring that it does. Then there are service providers, which is an object or objects that perform specific work and offer services to others on demand. For example, performing a certain function or carrying out a certain algorithm. Then there is controllers, an object designed to make decisions and control a complex task. So that coordinates what are the things that we do one after another. That takes the control away from the user and lets the system do something and then gives it back to the user. And then there is a coordinator, an object that doesn't make any decisions, but in a rote or mechanical way, delegates works to other objects. One example for that is the mediator pattern. And then there's an interfacer, an object that transforms information or requests between distinct parts of a system. The edges of an application contain user interfacer objects that interact with the user and external interfacer objects, which communicate with external systems. Interfaces also exist between subsystems. So the facade pattern is an example of a class designed to simplify interactions and to limit clients' visibility of objects within a system. within a subsystem, to be specific. So remember how we're trying to encapsulate information and hide it from the parts of the system that are not relevant. That has been done by interfacer objects. And then Rebecca moves on to existing design and heuristics. She says role stereotypes are also useful when taking a broad look at an existing design. So if you're curious about what role stereotypes predominate and how they interact, you're going to learn a lot about the structure of the system. One good way of finding out about that is to ask, are there recurring patterns and themes that you can find? And if you follow the design heuristic, make objects do something with what they know, then experienced designers often blend role stereotypes to make certain objects more intelligent. Their designs often do have information holders that compute. You will find service providers that cache information, using it to improve performance or give clients more control over their operations, and carefully crafted structurers that answer intelligent questions about the objects they organize. And then there are 3 more points in the article. One is about uniqueness. So it's important to differentiate between an entity and its value. The entity will always need an ID. So when we talk, for example, modeling cars, then 2 people could have the very same car, same color, same year, same manufacturer, same engine characteristics, and to differentiate them, they need an ID. Then there's quantities. So-called whole value classes can represent a quantity of a very specific kind. So instead of only having a number, we will have a characteristic that is domain specific. Instead of 33 as a temperature, you would model temperature as in Fahrenheit or as in Celsius. And you'll know that's a big difference. 33 degrees in Fahrenheit is really cold. 33 degrees in Celsius is really nice and warm to actually pretty hot, depending on who you talk to. And then last but not least, there is use and impact. Understand larger context of the class. For example, what kind of abstraction is being used here? Are we abstracting from some more specific cases? So those are the main points that Rebecca had in her talk. And here, just a little bit more visual representation. When you look at role patterns in software designs, then through the labeling of roles, we can find regularity in the graph patterns. So for example, in that class diagram that is on the left here, gotta get closer to the screen to be able to read it, the functions implementation, the blue one, that's the controller. And then we have several service providers highlighted in green. So the power level, the clock, the timer, and the function key implementation. Now you had a good view of my nose, sorry. And here is an illustrated version of how Rebecca illustrates the stereotypes, or a couple of the stereotypes that she presented in that article. You can find the original slide and the full slideshow at slideplayer.com under the link that is at the bottom of this slide. So 2 examples here are the information holder. It holds facts. It is characterized by what it knows. And examples for that could be transaction records or kinds of accounts. And then there is structurer. It maintains relationships between others. It is characterized by who it knows and what it knows about them. For example, an order. A little bit more recent work by Rebecca that you might also be interested in looking into, because she does cool stuff. She was also very involved in the Agile community. I'm sorry, I can't recall off the top of my head whether she was one of the original signers of the Agile Manifesto, but she's done a lot of work in that area. So you can listen to the Agile Uprising podcast, episode number 40, to hear her talk about Agile architecture with Martin Fowler. And then you can also listen to her talk about How can you know whether your Scrum Masters are effective? And that link is provided at the bottom left of the slide. So go check it out. The design habit that I would like to remind you of today that seems to be the most relevant for the module that we look at today is that experts draw the solution as much as the problem. So you want to make sure you spend sufficient time modeling the domain that your problem resides in before moving into the solution. That's not entirely correct. Not just sufficient time before you move into the solution, but also you want to make sure you iterate enough between those two. So you want to make sure you get a good grounding in your problem domain before you start thinking about the solution. And then after you think about the solution, come back to the problem domain, think more about that, and then keep going in iterations to further refine and to better understand. So experts know that their understanding of the design problem and their understanding of its solution inevitably deepen and co-evolve as they design. That's the iterations. Experts therefore draw the problem as much as they draw the solution. By moving back and forth, they not only ensure they both stay in sync, but also explicitly use advances in the understanding of one to drive advances in the understanding of the other. So keep that at the back of your mind for today's topic. For domain analysis, in software engineering, domain analysis or product line analysis is the process of analyzing related software systems in a domain to find their common and variable parts. It is a model of wider business context for the system. And the term was coined in the early 1980s by James Neighbors. Who of you was around? I've been around since 81. So it may have just been around then. Domain analysis is the first phase of phase of domain engineering. We got to analyze and understand the domain before we can start modeling it and before we start engineering it. It's a key method for realizing systematic software reuse. So the term domain engineering, you're going to find that a lot in software product lines. And while you may say now, wait, software product lines, can we first develop one system at a time? Granted, yes. You will be thinking a lot about product lines as you move into industry in whichever area of work. And the reason for that is that a lot of the systems that we develop these days have to run on different end platforms. They have to run on different types of phones, on different types of computers, in different types of cars. So there is some basic commonality in between all of those: mobile phone, laptop, car. And there are significant differences in the individual products, which some people get very passionate about over those differences and then argue that one product is so much better than the other one. We're not going to get into that right now. What I'm trying to say is the underlying commonality, that's the domain engineering. And then you put the specific products on top of that. So domain analysis procedure produces domain models by using methodologies such as domain-specific languages. Sometimes also feature tables, facet templates, and generic architectures. And they describe all of the systems in a domain, and several methodologies for domain analysis have been proposed. So remember that term domain-specific languages. Domain-specific languages are the terms that are used to model concepts that reside in a specific application domain. For example, when we try to engineer cars, there is a language called AutoSAR. I guess I'm pronouncing this a little bit German. I think it also came out of a German standardizing committee, at least in part. So that domain-specific language makes sure that all automotive original equipment manufacturers, those are the people who build the cars, as well as all their suppliers who build all the accessories and the parts for it, that they all use the same terms for the same things instead of their own synonyms. And that makes interfaces in between their subsystems easier, and it increases reuse. The products or artifacts of a domain analysis are sometimes object-oriented models represented in UML. That's what we are going for. There are also data models that can be represented with entity relationship diagrams. Maybe you've done those in the past, maybe not. We're not going to specifically do them in this lecture. If you ever come across entity relationship diagrams, then just know that they essentially capture the same type of information as a rather abstract class model. They focus on the data part of it. Software developers can use these models as a basis for the implementation of software architectures and applications. And this approach to domain analysis is sometimes called model-driven engineering. And that's what this course is about. We do model-driven engineering here. A domain model then captures the most important types of objects in the context of the business. The domain model represents the things that exist or events that transpire in the business environment. This was said by Ivar Jacobson. Who? Ivar Jacobson. Ivar Jacobson is the second one of the fathers of UML. Remember who the first one was? And he is just the first one because he showed up first in the lecture, not because I'm giving them an order. Yeah, that was Grady Booch, correct. So Ivar Jacobson is the second one. And who's this third one? James Rambeau. Yes. In software engineering, a domain model is a conceptual model of the domain that incorporates both behavior and data. In ontology engineering, a domain model is a formal representation of a knowledge domain with concepts, roles, data types, individuals, and rules, typically grounded in a description logic. Now here's a first example of a domain model in UML as a class diagram. We see a person, we see a company, we see a car. Okay, let's see, what are all the elements in here? What can we read out of here? Are those software objects? Nope. I know it says at the bottom of the slide, domain objects are not software objects. What they are is a representation of real-life conceptual objects. So in the class diagram that we model for a domain model, we're only going to take the entities that exist in the real world and stick them into a representation of that conceptual object. We're not yet at the software objects. Later on, there will be additional software objects that enrich those diagrams, but we're starting with just representing the parts of the real world that we need to represent in our system. So person, car, company, good. Those are domain classes. And then we have associations in between the domain classes. If you look at the top one, between person and company, you see that there is an employee-employer relationship. And it sometimes feels a bit backward how to read it. So a person is an employee by the company, and the company's employer, no, the person is employed by the company. The company is the employer of the person. You get what I'm saying in that make sure that the right role name is at the right end of the relationship, because sometimes it gets kind of confusing in our head as we read it out loud. And then you have a multiplicity for that association in both directions. So what's the multiplicity here? A company can have one to many employees, and a person can be employed with a company or not. And then we have a second relationship, which is the owner of a car. And in this direction, you could say, well, why is this only one directional? A person can own several cars, or none, but the car doesn't know its owner. Well, pretty sure my car didn't know its owner when I still had one. So that is a design choice of how I want to represent that. if I want to make that accessible, or if car by itself is just a little more encapsulated of an object and I can only access it in one direction, access the relationship in one direction. And then within the attributes, within the domain class, I have the attributes. So for person, I have a first name and a last name that is both a string, and then I have a salary. And for some reason, the salary doesn't have a data type here yet. So that has not been decided on how to represent that. And then there can be additional rules that are specified in these little comment fields. Now, and in this case, the rule says if a person is not employed by a company, then they do not have a car. Harsh. Okay, maybe they don't need a car. So first, understanding of what these class diagrams look like. Here's a slightly more encompassing example for a domain model, and that's for a health insurance plan. So you see the insured person, top center, and then there is some demographic info associated with it, and then there is an address. And what's that little diamond-shaped thing? That means that object is dependent on demographic info. If demographic info doesn't exist, address doesn't exist either. For the insured, we have a generalization. So he has two specific subtypes. One is subscriber and one is dependent. And then the insured is enrolled in a plan, going to the left. The plan has deductibles. The plan has associated a payer. And it has a benefit set. The benefit set has a service, and that service can have in-network and out-of-network coverage. And this also makes clear that it is a US health insurance plan. How do I know? Because before I moved to the US, I did not know what in-network and out-of-network coverage even meant. So here's a brief background. Many insurance companies have a specific set of providers of specific doctors that they work with. That's what they call their in-network. However, if I happen to know a really good specialist in the area that I need to go to, that I need attention in, medical attention, and he does not work with that insurance company, that's considered out of network. And depending on what insurance policy I have, that may mean that it's covered or not, that I have to, then I would have to pay out of pocket for it. Okay, with the demographic info, we also have a provider associated, because usually you have a general practitioner that you go to first. And there can also be a hospital or a physician or a third party. Good, so just slightly more extensive example. And then, as you can imagine, domain models can become as complicated as you want, or as complicated as cannot be avoided. So what do we look for when we do this? There are things, for example, books, libraries, garages. So those are very concrete things that we can touch in the real world. And then there are other things like order, payment, reservation that we cannot touch in the physical world, but, well, we can touch a piece of paper if it's on there, but the concept is a little more abstract. So those are types of things. And then there is actors, there is persons, but there is also roles and organizations. And then a couple of examples for that could be patient, doctor, driver, author, seller, censor. Wait, yes, remember, actors can also be other systems. And then there's properties of things and actors. There's color, there's location, there is name, amount, volume, currency. Properties, wait, what are properties? Yes, properties are probably going to turn into attributes. So for the properties, you want to do an extra step in your analysis, and we'll repeat that a little later on in the slide with the steps that you want to go through. The things and actors, they will become classes. The properties of things and actors sometimes turn into attributes if they are simple, or if they're more complex, they can turn into other classes. And then there is relations between the things. For example, an is a relationship and a part of relationship. A couple of more typical things to look for are actions and events and the relations in between them. For example, repair, pay, order, failure, turn, eat, move. So atomic events, atomic actions. And then there is domain logic. There are rules. There are causal relations between actions. For example, passing a deadline causes a fine. Have you ever read the Hitchhiker's Guide Through the Galaxy? It's a really old book. It is freaking cool. I think it was written in the 70s. And Douglas Adams wrote it. And Douglas Adams had this really cool quote about deadlines. He says, "I love deadlines. I love the swooshing sound they make when they fly by." Okay, back to domain analysis. There is also processes. There's relations between actions and events. Those can be, for example, business processes, they can be information flows, or they can be control flows. Now, what makes a good analysis? There are 4 really important points here. One is correct scope. What happens if my scope is too small? Well, then I'm missing really important elements in my analysis. What happens if the scope is too large? Well, I'm just never going to finish modeling because it means I'm trying to represent too much of the real world in my model. Second part, complete. Oh, how am I going to know if I'm complete? That's a recurring trouble. You might remember that from requirements engineering. When are the requirements complete? Well, when we have captured everything that's important and when we have talked to everybody who matters. Okay, and how do I know that? Sometimes we can help ourselves using checklists and using another set of fresh eyes and getting a new perspective and putting things away for a few hours and then looking at them with fresh eyes ourselves. And sometimes we only find out at the next stage when we're like, oh, wait, we overlooked something, we need to go back. So yes, that's a criterion, and it's going to take your judgment to assess it. Consistency is also really important. That's the third one. So we want to make sure that our domain model is consistent in the sense of that information exists in only one place on one thing, and that there is no contradicting information. And then last one, that it's systematic. We want to structure it as good as we can. We want to make it as simple to help understand what's going on as possible. That's what we do in software engineering. We try to simplify things, especially for the user. So we try to make things look really simple for the user and hide away some of the complexity. And for that, we need to make it really systematic. And this analysis is typically performed by an expert in the domain. What does that mean? If I, as a software engineer, get asked to build a financial system, then I better go talk to a finance expert if I am not a finance expert myself. So that very same domain analyst in finance or banking would then also not automatically be good doing domain analysis in automotive, because they may or may not be interested in automotive. They may or may not have ever looked into what it takes to build a car or even to repair a car. So try to get as good a domain expert to talk to as you possibly can. let's jump into this. Let's just try it out ourselves. So it's Tuesday afternoon and Sarah walks into the office of the Superfly travel company on Avenue in Gothenburg. She opens the door and draws a ticket. That's how you know you're in Sweden. You come in, you draw a ticket with a number on it, for those of you who are not from Sweden. And the number tells you when it's your time to go talk to the person at the counter. Sarah is 24 years old and would like to visit her grandmother Anna, who is 77 years old and lives in Rotterdam. Sarah is interested in booking a flight from Gothenburg to Amsterdam. When driving by road, the distance from Gothenburg to Amsterdam is about 1,096 kilometers, very roughly. From Amsterdam, she will take the train to Rotterdam. Sarah is known amongst her friends for being very flexible. However, she has a preference for pink airplanes. Don't judge. The assignment for this is create a domain model. How are we going to get started on that? What do we say we'd have to start looking for? Things. So let's just start with that first sentence. It's Tuesday afternoon and Sarah walks into the office of the Superfly travel company on Avenue in Gothenburg. So there is a company, a travel company, but we're abstracting from that in a step. A company that has an office in a specific location, and it has a customer, and that customer has a name. So the customer is the abstraction of Sarah. And apparently we are not quite sure how to spell her name. So the notation for this one is on top we have the thing, and then underneath we have the properties, and then underneath we can have the capabilities. We haven't talked about those capabilities yet, but those are the things that that person can do. Next one, she opens the door and draws a ticket. Are we going to need to model the door in our system? Probably not. That has nothing to do with the business processes that we can support here. Is the ticket relevant? Maybe. Sarah is 24 years and would like to visit her grandmother Anna, who's 77 years old and lives in Rotterdam. So from Sarah, we take customers have a name, that's a property, and they have an age, that's also a property. Why does that matter? 24, 77. Well, one part that matters is she's an adult, so she can take decisions on where she wants to travel to, and there are no special requirements for accompanied travel. Say if she was of minor age. There are a lot of car insurances that for rental cars will only take a driver over a certain age. Otherwise, they're going to charge you more for the insurance coverage. And then for the grandmother, if she was to travel, there are probably a bunch of senior discounts that she could get. So therefore, it makes sense to model the age along for the customers. In this case, the grandmother and the age and her location are not essential for the travels. Sarah is interested in booking a flight from Gothenburg to Amsterdam. So the customer is interested in a booking. And because we don't want to model interested, for the business logic, it matters, is she going to do a booking? And if she does a booking, then she will have a booking, and that's what we model in the system. And that booking has an origin and a destination. Good. A little more. She's booking a flight from Gothenburg to Amsterdam. So the trip can have several legs, because we also remember she still has to go from Amsterdam to Rotterdam. And you see that the star notation for the multiplicity means either 0 or more. So it can have 0 legs or it can have several legs. Good. Sarah's interested in booking a trip from Gothenburg to Rotterdam, flying from Gothenburg to Amsterdam and then taking the train from Amsterdam to Rotterdam. So we have 2 legs, 2 instances of leg here. Leg 1, Gothenburg to Amsterdam by flight, and leg 2, Amsterdam to Rotterdam via train. And both of that can be expressed in the class on the left. When driving by road, the distance from Gothenburg to Amsterdam is about 1,096 kilometers. Not so relevant yet. Maybe it could come into the pricing later on though. And this data can be derived from existing data, so it may not need to be included in our system. Sarah is known amongst her friends for being very flexible. However, she has a preference for pink airplanes. Customer has a name. Where did the age go? The age went away. Well, and they have a preference. Well, let's say on this slide, we're only modeling what we're taking out of the slides. We have the name and we see the preference. Reminder, the notation was we got a thing and that we have properties and capabilities. So if we now put all of that together, then we can say the company, the travel company, has an office. The office has a location. That office has customers. Each customer has a name, a birthday, and a preference. Wait, why are we modeling a birthday? I thought we modeled the age. Yeah, but then we'd have to update the age all the time, and we'd probably be outdated most of the time. So it makes more sense to model the birthday that does not change, and then infer the actual age as a customer comes into the office again. The customer has a booking. The booking has a trip. The trip has 0 to several legs. And each of those legs has an origin, a destination, and a transportation of a specific type. So far, so good. Is there anything missing from the analysis? What came up that we haven't really put into this model yet? What do we not know about? That's always the most difficult question. Like, what do we not know about? How am I going to get the answer to that? So what we do not have in a class model, and we can't have to a certain extent, are dynamics and behavior. So we can write down certain capabilities if we wanted to. Those are the methods in a class diagram. But we can't really describe the behavior that's going on in the system that is hidden behind action names, and not the dynamics either. And we do not have the business logic either. So repeating or recapping how to develop a domain model. You make a list of candidate domain classes. And for that, you identify the nouns. You can just underline them either in a textual requirement specification or in your UML use cases, in your use case descriptions and the scenarios. And then you draw these classes in a UML class diagram. Add brief descriptions for those classes. Identify any associations between the classes that are necessary. And then decide if some of those domain classes are really just attributes. For example, if you wrote down a separate class for age, then you might reconsider and say, oh, you know what? That's really just an attribute. I should just model that as date of birth. And then where helpful, identify the role names and identify multiplicities for associations. So the role names were the things that were written on the end of each association arrow in between two classes. Add any additional static rules as UML notes that cannot be conveyed with UML symbols. So a little reminder of our example from company, person, and car. The role that was written down was a person can only have a car if they work for a company. So that's a static rule that we don't know how to express in UML, but we can write it down here. And then group your domain classes by categories into packages. Remember that rule of thumb of how many items we can keep in our head at the same time. It's 7 plus minus 2. That's what Grady Booch also wrote in his book. I don't remember the original scientific author of the study right now. But that's your visual rule. So if you have 25 domain classes in your model, you look at it and you might get overwhelmed, or you present it to a new stakeholder or a new colleague and they're like, whoa, too much. So instead, you try to group them, make it simpler to perceive that way. And then just another word on sources and quality. So where do we get that info from? We're going to elaborate that from business case analysis, if we have one. That's not part of this course, so that is something that you will see later in companies and that you maybe get an insight to in another course. But at the end of a business case analysis, that's pretty much the high level requirements before you ever really talk about a software system. It can be written up in text, it can have diagrams to support it. It is fairly similar to a requirement specification, but usually at a higher level of abstraction and more focused on the business feasibility, the business potential outputs, and how they're gonna work in the market. And then you can get stakeholder input from goals, from constraints, about just domain knowledge in general. And then you can do your own background research. And you have your requirement specifications, your use cases, maybe textual requirements. So all of those can help. And then for quality, the most difficult part is the completeness. We've talked about consistency and we've talked about choosing the right scope, and then there's the completeness. So you want all important concepts of the problem domain, you want adequate attributes, and you want all important associations in between them. And the best way to find out whether that is true is to let a couple of other sets of fresh eyes look over it and to talk to another domain expert to make sure you have them. A little reminder of your design habit. Experts draw the problem as much as they draw the solution. That's also how you get complete. So by going back and forth in between your problem modeling and your solution modeling, you get to understand better and you become more complete. Let's move on to letting you do the exercise. I'll walk you through one. So sticking with our running example, find classes in one of the use case descriptions that you previously did for the amusement park. Like, take those use case scenarios you wrote down. You can start with the use case overview diagram and write down those. And then you can move on to the use case scenario descriptions and pull your domain elements out of there and make your domain class diagram. Or if you like, you can go look up what the ER diagram notation is and do it according to that. Second exercise, pick a random piece of object-oriented code and re-engineer a class diagram from it. So go back to something that you did last semester, last year, and re-engineer that out of your own code without looking at old diagrams if you had some. Or go to an open source project, go to github.com, find a project that you like, pull code out of there, and then re-engineer a class diagram from it. I know I can tell you all about these exercises and I can walk you through more of them. You're really going to learn something if you just go try to do it yourself. Go. And I'll see you soon. Thank you so much for watching.